Okay, now let's we know something on lossy compression. Okay, so lossy compression. Let's start with the comparison with lossless compression. If you can understand this, so you know that in lossless compression algorithms do not deliver compression ratios that are really high enough. So usually maybe 1.2, 1.3, this kind of compression ratio we have. So therefore, most multimedia applications, they basically require lossy compression, and that's the main focus basically in compression for multimedia. So lossy compression, as you say, that the compressed data is not the same as original data, but it's a close approximation of it. We had this original data, after the compression, this is we are say lossy compression, we get the data. So but this is not exactly the same as this, but it's a closer approximation. And definitely it provides much higher compression ratio compared to this lossy compression, compared to lossless compression. So this is basically lossless, not lossy, right? So this one just you just correct that one. And if you see that file formats, for example raw file format, MOV format, ALAC format, these are basically lossless file format. And on the other hand, JPEG, MP4, MP3, so these are lossy file format. And definitely, as you understand that, yes, these are the most suitable format that we use for multimedia applications. And this one, for example, raw file is used just for as a very source file. Okay, so based on that, the other file we prepare. And the applications for lossless algorithms are text processing, spreadsheet, zip file, those things. And for lossy compression, generally we use for audio, video, and image. So when it comes to lossy compression, definitely one thing's coming to our mind, that is called distortion. Now distortion, we need to measure somehow. Okay, so think about this image or let's say video frame, and it looks distorted, right? Now how we can mathematically quantify this distortion? This is some sort of distortion. So definitely there are two approach of distortion measurement. One is quantitative measurement and another is perceptual measurement or perceptual distortion. Now perceptual distortion, that you just see and how you feel. So that kind of things are perceptual. And the other is quantitative. You basically mathematically you measure that one. So let's say mathematically we measure, if we measure distortion, there are several metrics called distortion measurement metrics. So first distortion measurement matrix is mean squared error. Sometimes we represent mean squared errors with the sigma square. Okay, now mean squared error generally can be written in this way. That is, let's say we have some data called, let's say x1, let's say as a data sequence, x2 and up to xn, original data sequence. And let's say we compressed it and we decompressed it, and finally what is our output, or we can say reconstructed data sequence after the decompression. That means you compressed it, you store somewhere, and then you decompressed it. So let's say that data is y1, y2 and up to yn. So this is one sequence and this is the reconstructed sequence. Now what is the difference between these two data? So because this is the original and this is our reconstructed data, so this is the difference between these two data. Now the difference between another data is this one, and in the same way we just make the differences for between every data points. Now definitely some data points are positive, and this difference, some differences is positive and some differences is negative. Now what is the total differences or total error? This is also called error, right? What is the total error? So because some are positive and some are negative, so it is good that we measure these things. We take square of this one. Okay, we take square of each one, square of the error. So, and now if we just sum up, then there is no such problem. That if we just sum up the squared of these differences, so there will be no cancelling out from each other by each other. So to get rid of the sign of this issue, so we just took squared, but still square is a measurement of error, definitely. So anyway, so that is what it says, this equation. So it says that we just take difference and square of that. So that means this is our error, and we take square, so this is become squared error. And if we just sum up all the squared error, that means you just take any xn, and you just take their differences, you take square of that, you just took sum of that, that is from I equal 1 up to n, or let's say capital N, whatever. So n, so that means n equal, as we can say, not I, this is n equal 1 up to n, and then you divide by n. So that means what? This is your sum squared error. This is your sum squared error. Now when you divide by n, this is becoming your average squared error. Now average squared error, the average another name is mean. So that's why we say mean squared error. This is basically, it will be squared. So mean squared error is this one. Okay. So and that is, we say MSE, and sometimes we write this is as a sigma square. Okay. Now sometimes we are not really interested only in this mean squared error, rather we are interested in the relative. Let's say we have signal, this is our error, this is definitely our error power, but we are interested in also signal power, right? Because let's say if our error also can be think as a noise, this error, because this is an error, is definitely some sort of noise. Now compared to this noise or error, if our signal power is sufficiently high, then it doesn't matter, right? This error, it doesn't problem, it will not create much problem. So we are basically interested in something like called signal to noise ratio. You see, we are interested in signal to noise ratio. Now signal to noise ratio, it means signal power, it generally means signal power by noise power. Okay, noise power. Now this noise power, this is exactly, in this situation we can consider this one is basically our noise power. Okay, so we already know what is the noise power. What is the signal power? Now signal power we can think of like that. Let's say x is our signal, so we can think this is the signal power. So how to calculate this signal power? The calculation of signal power is very easy. We already know this our data sequence x1, x2 up to xn. What we do is just take square of every data terms. Okay, just take x1 square plus x2 square, and in this way plus xn square, and you just divide by by the data points, how many data points you have. So this is basically your signal power. Okay, sigma x square. So if you calculate the sigma x square, and then you calculate the noise, that is sigma d square or MSE, then you just divide these two, and then you get in this way. So this is sigma square by sigma d square. This is our SNR, or signal to noise ratio. Now this signal to noise ratio, very often we represent in terms of dB or decibel. Okay, so when we express something in dB scale or decimal scale, how to do that. This, let's say this is sigma d square. D mean differences. Okay, this is the exact sigma, but because of error, so we just write d. So what we do is you just take log 10 of this and multiplied by log. Okay, so this is how we represent if we are interested in decibel, decibel, dB, decibel. Whenever we compare something, it is always good to represent in terms of dB scale or decibel scale. Now how we do that? Let's say this is our number that we want to convert to dB scale. Just we take log 10 of that and then multiply by 10. So that's how we do. Okay, now more on dB scale we will study on in audio signal when we will study audio and audio compression at that time. But for this time being, it's okay. Now, there is another terminology, that will be coming little later. But first, we take an example. Let's say this is our, original data sequence, that is 54871, and let's say this is our reconstructed data sequence, and that is 54871. This data we basically, let's say, compressed it, and let's say we store somewhere, and let's say we decompressed it, and then we reconstructed sometime later. So that data is 4562. So this is our reconstructed data sequence Y, and this is our input data sequence, let's say X. Okay. Now in this situation, let's say we calculate signal to noise ratio. So definitely, because this is our decompressed data and this is our original data, so there is some differences, and we like to measure the distortion in terms of SNR. Now how you do that? So it's very easy. First, let's calculate the signal power sigma x square. Now signal power is basically, you see, 5 square, 4 square, plus 8 square, plus 7 square, plus 1 square, and then you divide it by 5. And if you do so, then I don't know how. So there is 25 plus 16 plus 64 plus 49 plus 1 divided by 5. So it's become 25, 16, 64, 49 plus 1. I think 155 divided by 5, and then become 31. Okay. So that's your signal power. Now how about the noise power? Now noise power is basically sigma d square. So that is the differences between 5 minus, because the differences between these two, and then you take a square. So differences between this is 5 minus 4, and you take square of that, plus differences between these two, again 5 minus 4, or actually 4 minus 5, and then you take square of that, and then plus 8 minus 6 square of that, and then 7 minus 6 square of that, and then plus 1 minus 2 square of that, and then you divide these things, divide by 5, right? Now if you do so, this becomes 1, this become 1, this become 4, this become 1, this become 1 divided by 4 and divided by 5. And then if you just do so, then become 1, 1, 2, 3, 4, 4, 5, 9, right? 8 by 5, that is 1.6. So that means this becomes 1.6. So if you just calculate this one, okay, 1.6. Now this we got this sigma square x square by sigma d square, and we take, because we will express in terms of dB, so we will take log 10 of this and then multiplied by 10, so that is 10 log 10 of that is 31 divided by 1.6, and this one if we just calculate it, so then you can find out that it is become 12.87, and basically this is in dB. So we calculated the signal power, and we know the signal power that we had is 31, and then we calculated the MAC, and then we saw this MAC is 1.6, and then we found out the SNR, that is just ratio of this one in terms of dB. This is becoming is 12.87. Now definitely you can do it yourself, some other examples or some things you will find out in assignments or something. Now let's understand this figure. This says that rate distortion theory. Okay, so it is basically a framework. Whenever we understand compression or transmission stuffs, we study this kind of things. It says something like that. This is the reciprocal relationship between your distortion and your information rate, or data rate. For example, let's say this is distortion in this axis, and this is, let's say, data rate or information rate that you are achieving when you transmit information or when you receive information from some systems or from some information source. So that is basically, let's say, R, this is rate as a function of D, this is RD. Okay. Now let's say, what is the information rate, when you have, let's say there is no distortion. Let's say if there is no distortion, what is the information you can achieve, what is the information rate you can achieve. Let's say dash information is h, okay. And then let's say what is the distortion. Let's say our information communication channel or our coding mechanism is such that we really can't transfer any information, or we can't understand any information from some system. So that means is distortion is so much so that is we can't receive any information, or in another word, at rd equals 0, our distortion become maximum amount of distortion, right? So let's say that distortion is somehow, we say that distortion is, let's say, d max, okay. And this is, let's say we are saying this is basically our r max. That is definitely at distortion 0, this is the 1, this is the maximum rate we achieve, and distortion max we achieve the minimum information, that is 0 information. Or when we achieve 0 information, it means completely we can understand, completely we can model that system in terms of maximum distortion. And in between, you basically is just a reciprocal or exponentially is fall down. So that means as distortion increases, our achievable data rate is basically decreases, okay. So this sometimes we need to play out. Now you see, what is this h? This is exactly the entropy. This entropy that we calculated in information theory, that's entropy. Now definitely how it becomes related with entropy, why that is a different things. We are not studying that one, but somehow I'm just saying. So this kind of framework, sometimes we make and trade off that what information we want to achieve from an information source, what amount of information we like to transmit by an information source with what amount of distortion. So this distortion and rate, we need to choose, we need to make some sort of trade-off between rate and distortion. If we like to have maximum rate, then distortion need to be 0, but it's really impossible. So maybe somewhere here, depending on your applications, you need to choose that at what rate, at what distortions you will allow. So with these things in mind, we will now study some other things. Very first important one is quantizer. Now quantizer is very important, and this is considered as one of the main source of the loss or distortion in lossy compression technique. In fact, this is one of the main problems in all digital systems. Now in real world, whenever we see an information, that is always analog in nature. So for example, if you see a photo, that light is reflected from the pictures into our eyes, into our retina. So amount of light is basically analog in nature. When we generate electric voltage, that is analog in nature. So but in computer systems, we convert that analog signal to a digital digital form, right? So that's called something called analog to digital conversion, or ADC, okay. So very appropriately ADC. So in ADC, we use this process called quantizer or quantization. So we see that how this quantization basically happens. So let's say our information from a real source that we see, maybe something like some analog source. Let's say the minimum is 0 volt, and let's say minimum is, I don't know, maybe this is better. Minimum is 0 volt and maximum is 1 volt, right? So it might be anything. It might be volt, it might be millivolt, but let's say more about number from 0 to 1. From the source, and it might take any values from 0 to 1. So it might take 0.1, it might take 0.112, it might take any values. So ideally it might take infinite possibilities, possible number of values that you have, possible values you might have from your information. But practically we can't keep track and consider all of these possibilities, all of this in every continuous possibility. We can in continuous manner. It is possible that even within 0 and 1, in infinite number of levels are there, right? But practically we consider very less number of levels, from 0 to 1, and that is somehow sufficient. So anyway, let's say that we divide these things. Practically what we do is just divide this from 0 to 1. Let's say we divide into 4 groups, for our example. Let's say 0, this one is 0.25 volt, and this one is 0.5 volt, this one is 0.755 volt, 0.75, and this one is 1 volt, right? Finally, so this is our let's say our division. Now what we do is, let's say any voltage or any input information that basically let's say come somewhere between 0 volt to 0.25 volt, let's say within this range, right? Any voltage that's come within this range, we represent, we assume that value is something like in between of these 2 levels. Now what is this point? This point is maybe let's say this is, if we make average of that, so it becomes 0.125. Similarly, any voltage that comes in somewhere between 0.25 to 0.5, we consider that value is 0.375, something like that. And any voltage somewhere between 0.5 to 0.75, that is something like maybe 0.625. And any values that comes, any input information that comes between 0.75 to 1 volt, that is we can consider as 0.875 volt, right? So this is an example. Just in this example, we consider 4 different levels. Okay. Now let's say this level we can represent digitally by 0, 0. This level we can represent by 0, 1. This level we can represent by 1, 0, and this level we can represent by 1, 1. In this way, the entire analog information we convert to digital forms. Now, this is very fine and it's working in today's world, right? So in this case, our ADC conversion, ADC that we are using, conceptual, and in this example is basically 2-bit ADC. Why 2-bit ADC? Because you see, for each level we basically assign 2 bits, so that's why we can represent 4 different levels. Now if your ADC is something called, let's say, 3-bit ADC, so that times you can basically represents or handle 8 different levels, right? So at that times you can divide 0 volt to 1 volt into 8 different levels. You have 4-bit ADC, then 16 you have 8-bit ADC, then you can actually represent 256 different levels, whatever it is. But let's say for this example we consider 2-bit ADC, and as such we consider 4 different levels, and the 0, 0 level is this one, and in such a way, right? This is fine, but can you see the problem here? The problem is basically I don't know how is red. Okay, red is okay. So the problem is, now think about that. Let's say your input comes somewhere here. So let's say your input from your image level or from for any electrical voltage or whatever. Let's say this is basically, let's say 0.1 volt. Now if this is 0.1 volt, we will not consider this is as a 0.1 volt, because we will consider this one is basically 0.125 volt. So your original voltage is 0.1 volt, but you are considering this one as 0.125 volt, because whatever voltage comes in between 0 volt and 0.25 will represent that one by 0.125 volt. So what is the difference between this? The difference between this is 0.025 volt. So this 0.2.5 volt we lost, or actually we basically not lose here, we basically add as a noise with this original volt, right? So and then we have this one. How about if we have let's say our input voltage, let's say 0 volt. Even at that time we will consider this 0 volt as 0.125 volt. That means this is the worst case situation, right? In this worst case situation, that you are basically having the problem of entire 0.125 volt is basically your noise, right? So that means that because of this leveling, we are having some problem, right? So, and why this, this noise is coming? Because we just, level this one, this leveling, that whatever voltage comes in between 0 volt to 0.25, we will consider this one as 0.125, and whatever voltage comes in between 0.25 and 0.5, we'll consider this one as 0.375. So in this way, we are basically quantizing our information. Quantizing means we are, we are providing very specific number of levels. So that called quantized. So this is quantization level, 1. This is quantization level 1. This is quantization level 2. This is quantization level 3. This is quantization level 4. So these are 4 different quantization level. And because of these quantizations, every sample, whenever a voltage comes in, for every sample, let's say for every sample in when we do, or every pixels that we assume that has a physical voltage, but we are considering this one is another voltage, and we are having some noise, or we are adding some more noise, or we are losing some information. Either we are adding noise, or we are losing some information, whatever we can say. So this is the problem, and this is the main source of in any analog to digital conversion, and even in this these things that we are studying, the image. So now think that when we have the maximum voltage is, let's say, 1 volt, and the minimum voltage is 0 volt, and in this particular examples we assign 4 different levels. So what is the step size? That means from one step to another step, what is the differences between that two? That is become 0.25 voltage, right? So for example, from this step to this step, or from here to here, from each steps we basically have 0.25. This is called step size, something called step size. Now, what is the worst quantization error for every sample possible? So that is then 0.25 divided by 2, that is 0.125 volt. So this 0.125 volt is the worst case situation. But generally this doesn't happen. Normally what we have is mostly our values remains somewhere around this 0.125, 0.375, but some values coming from here, some values coming from here, those are extreme values. So now you see, this is called quantization error. So quantization error, now in a nutshell, how this is happening: we have an input voltage from here to here, let's say 0.1 volt, or maybe any volt, or maybe minus 0.5 volt to plus 0.5 volt. Okay, so whatever it is happening, we are just dividing into some specific number of levels, right? And that is our 1 level, 2 level, 3 level, and 4th level in this way. Because of this is called quantization, and this quantization coming up with some noise and error. Okay, so now these quantizations basically have different types. Now one type is uniform quantization, and another is non-uniform quantization, and there is another category called vector quantization. Now let's understand what we mean by uniform quantization and what is mean by non-uniform quantization. Now, uniform quantization is something like that. Let's say what we do is, let's say in this range, that is from 0 volt to 0.5 volt, let's say we will divide this this range into 4 different levels. Okay, 4 different levels, this one, 4 different levels. This is 1, 2, 3, 4. Now how about, let's say the upper half in this one, let's say we divide this range into something called, let's say maybe 12 different levels. Okay, so that means, and I don't know, maybe this one, let's say there are 12 levels. So what will happens? So in this range we use only 4 levels, and in this range we use 12 different levels. Okay, and so these sorts of division grouping, if we do, then that is called non-uniform quantization. And the one that we did the example when we have that all in everywhere we have equal distributions, so that is called uniform distribution. Now why we need this non-uniform distributions? The reason is sometimes our signal level is this, that in the low input range we have most of the samples, let's say we have the less or the minimum voltage level, okay. So and some of the samples might have higher values. So that's why what we do is we can resolve this lower levels more. So to resolve signals, those minimum signals, what we do is we can have more levels in input in the lower levels and less number of levels in the upper values. Or sometimes it is vice versa, it is opposite, that maybe depending on our applications, that maybe sometimes it happens that most of the voltage are coming somewhere around here and around higher values, and less number of samples coming around lower values. So at that time it is good idea that we can differentiate these values more and these values less. So this is called non-uniform concepts, okay. But whatever, either uniform quantization or non-uniform quantizations, what we are doing in input, we have one value, definitely it's coming originally from analog point, but let's say one value, and then we are mapping this one value to another value, right, another value that we are mapping to. So that we are saying maybe 0.1 volt originally, but we are considering this as 0.125. So this is one-to-one mapping. So because of one-to-one mapping, this one-to-one mapping sometimes doesn't work well. So what we can do, rather let's our input one sample, two sample, three sample, four sample, maybe these four sample together we can mapping to another maybe two sample or four sample. When we do this group wise mapping, maybe one might be in error, but other three is in good mapping. So that's why this is called vector mapping or vector quantizations. So these vector quantizations, we will see that how that become advantageous, okay. And there is a theory in that, again the Shannon worked on this works. So they say that vector quantization always perfects better, okay. So form vectors of input samples by simply concatenating a number of consecutive samples. A number of consecutive samples we will use to decode to another consecutive samples in the output. So the one that we saw, this non-uniform and uniform, that is called scalar quantizations, because that is sample to sample. But when we assign when we work with multiple sample together, that's called vector quantization. And we will see one example of vector quantization, how it works. So in this example, what we are essentially saying is, let's say now we have four vectors, okay. We have four vectors, and the first vector is 0 0, and the second vector is 2 1, and the third vector is 1 3, and the fourth vector is 1 4. We can also say that maybe this is the first code word, and this is the second code word, this is the third code word, and this is the fourth code word. So these four code words forms a code book, okay. So either way we can consider, it doesn't matter. And you can also see that in this example we are using a vector of member 2, right. So that means two-dimensional vectors we are considering. So at each vectors we have two samples. That's what it means. Now we see that our input source, okay, let's say from our input what signal are coming. So let's say from our input the signals coming is 0 1 2 3 2 0, like this, okay. This is our signal that coming from the source itself. Now because we are using two sample vector, So that means we will be considering these two samples first, and then these two samples, and then these two samples. Now see, so from the source we are having, the very first two samples. So this is this one, 0 and 1. Now definitely we will convert this as a vector into our predetermined vectors, because in our quantizers we only have these code words or this code book. So now whatever vectors comes in, we'll choose one of these vectors from here. So that's the simple thing. It's the same as that we did in scalar quantizations approach. There, whatever values comes in, we just mapped to one particular samples. But here, whatever vectors comes in, we will just map to that particular code word. Now see this 0 1. So which one from these four vectors is closest to this one? So this we'll have to find out, right? So the very first vectors that we have in our code book is 0 0. Now can we replace this 0 1 with this 0 0, or which one? So we'll have to find out the distance. Now see, so the very first one that we have is 0 0 here, right? So our code word, the first code word is 0 0. Now can we find out the distance between these two? What is the distance between these two? Definitely we can find out this distance is, so you see, we just take the very first sample, that is 0, and this is 0. So that is 0 minus 0 is square, and then what is this one? This is 0, and this is 1. So 0 minus 1 is square. So it is just we are calculating the length or the distance between these two vectors. So this length become 1. I mean, it's somehow some sort of Euclidean distance we are calculating. Okay, so then this is 1. Now what is the distance with this one? This 2 1 and this vector. What is the what is the distance between these two? This is also very simple to calculate. That is 2 minus 0 is square plus 1 minus 1 is square, right? So just we take the first sample. So first sample here is 2 and here is 0. So 2 minus 0, and the second is 1 and the second is 1. So 1 minus 1. What is this distance is then? So this distance become 4. And how about the third one? What is the distance between this one and this one? So this is again, it is very simple. 1 minus 0 square plus 3 minus 1 is square and equal 5. And then what is the distance with this one? This one already I have calculated here. So this is 10. So this is that much simple. Now see, this distance is 1, and the second, the distance with the second code word is 4, and the distance with the third code one is 5, and the distance from the fourth code word is 10. And ultimately, this code word provide the smallest distance. So we can say that this 0 1 basically closest to 0 0 vector. So that means, see, we had 0 1 from the signal source, but now because of our vector quantizations, we must choose one vectors from there. So we choose the closest one is this one. Now what is the closest one for this one? This 2 3. So the closest one, this 2 3, again you can find out this one, and then you can see the closest one with these vectors is basically this 1 3. Okay, closest vectors with this one will be becoming 1 3. You can calculate the distances, and then you can see again in the same way. And then what is the closest distance with these vectors? Okay, these vectors. So because we are considering every 2 2 2 2, right? So we can see the closest one with this one is this one, that is 2 1. Okay, this is 2 1. So that's it. So we done. So we had just continuous signals from the signal source, and in vector quantizations now we have these vectors, right? So ultimately our output signals then become 0 0 1 3 2 1. So this is the quantized signal, and definitely this we did using vector quantizations. So this is that much simple. Now see again, we can think in this way that this is this one is our output, I mean quantized signal, that's fine, but this was our original signal, right? Now definitely we see there is a differences between these two. If you see that what is the differences between these two, you can easily compare. For example, so let's say we just take this one 0 minus, let's say the very first one is 0, right? So that means, so this is become 0, so this is no problem. But however the second was 0 and this is minus 1, so 0 minus 1, that is minus 1, and the third one is 1 minus 2, that is 1 minus 2, this means minus 1, and then 3 minus 3, that is 0, and then again difference 0, and then again difference 1. So you see, so this is 0, so this is 0 minus 1 minus 1 0 0 1. So this is basically the differences between our quantized signal and the original signal. So we can say, so this one is basically our quantization error. So again, as we understood that there would be some error when you do the quantizations, so same as here, we have this quantization error. So, and this quantization error we can't avoid as far as we do the digitization, as far we try to save our memory space and various other things. So I hope that you understood these things. So this is where what I explained. So you can also see the interpretation in this way. Now we talk about these things, that is transform coding and DCT, that is discrete cosine transform. Ultimately we like to study that how JPEG works, JPEGs or JPG image. So how this JPEG transformation, JPEG compression works, so that we like to understand. Well, definitely this is a huge topic, and there are very deep mathematics and signal processing things are associated, but for our things we don't need that much details. Just we will see a perspective that how JPEG works. Okay, so we don't need the very dig down details. So JPEG, that's the main things of JPEG is basically there is called DCT. Okay, JPEG joint photography expert group. So this is basically not an image processing things. This is basically standard. Standard means they have a set of guidelines and process or set of rules, protocols, how we do certain things. The certain things in this case is image compression. Okay, so and one of the core things to understand JPEG compression is this DCT, that is discrete cosine transform. Okay, so let's understand what we mean by discrete cosine transform. Now think about this. I mean, to start that one, this very rough and kind of very preliminary things and calculations will be helpful for us. Now let's say we have a let's say a gray level image. And in that gray level image, let's say we are talking about this, just a very particular dot. Can you see this dot? Okay, this very small dot, or let's say this area that's indicated by this a small segment of red line. Let's say we are thinking this one. Let's say at this there are so many pixels here, right? So let's say first how many? First few pixels are like this. Okay, let's say 72, 70, 65, 65, 66, 68, 72, 75, 80, 84, 84, 89. Okay, so these are our first few pixel values. Now, so there are this number, right? So how many numbers actually? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 numbers, or we can say 12 pixels. Now see, these 12 numbers, our aim that we really need to store 12 bytes of information, right? 12 bytes of information to represent this 12 number, to store these 12 numbers, or to present these 12 numbers. Now, is there any mechanism that we can store less numbers, but still we can understand and we can recover these numbers? And the answer is yes. So let's say that one way to do so, one perspectives of understanding that whether it is possible is this one. Okay, so think about like this. Let's say what is the average values of these whole numbers is 72 up to 89, and if you calculate the average numbers become 74. So this is, so if you can see the graphically, the 72 is basically, let's say this one is the 72. Let's say here is somehow, maybe I don't know, maybe as you go forwards, right? Let's say x dimension, or let's say distance d dimension, and whatever it is. And this is the value, the pixel values in this y-axis. So first number is 72. So this is the 72. That is small dotted, okay? And the next number is 70. So that is the 70, then 65, then 65, in this way up to 89. And then if you just, draw a line, and then going and passing through these, points, then maybe, this zigzag line we can see. Okay. Now we just took the average of these numbers. So the average is 74. And if we just draw that average line, so definitely, because this 74, this is a constraint straight line, right? So that's the red line. Okay. Now think about, sine x, cosine x, or cos sine x, cos x. Let's say cos x. How cos x look like? I mean, geometric things. Why we are suddenly saying sine x, cos x? The reason is we will know these things. This has a great implication. So this is basically cos x. You see, this is the cos x diagram, if you know it. And if you multiplied this cos x, by 3, so definitely that is points multiplied by 3. So this one is 3 cos x. Okay. So let's say there are 3 cos x. This one is 3 cos x. Now how about if we just add up this 3 cos x with this 74? So that means, this 3 cos x was basically, rotating or oscillating around this 0 line, right? This 0 line. And now this line, if we just, oscillate around this average line, it will be look like this one, you see. So that means our red line was 74. And then now, this red line is oscillating around this 74 because we just add up this 3 cos x. So in other words, we can just, add every numbers with this 74 and this one. So 74 plus 3 is 77. So this is basically 77. And you go at every point you add up, then you just come up with this red line. Okay. So this is, we are saying 74 plus 3 cos x. Now, that what is the sine x? So sine x is basically in the shifted version of cos x. You know that if this is our cos x, and if you do the 90-degree phase shift, then we will be having sine x. So this is the sine x basically. Now how about if we just multiply 10 with this sine x, so then it will be our, let's say, 10 sine x. Okay, so then let's say this somehow that 10 sine x we just subtract from this 74 plus 3x, or we can say we just add 74 and then 3 cos x, and then shifted version of our cos x we just add up, okay, with multiplied by 3. So ultimately we just end up with this one, the 74 plus 3 cos x and minus 10 sin x. Then we will have this red line, you see. But think about what I'm trying to say. Now you see this red line is almost resembles our original this line, right? So in other words, let's say we had this number 72, 70, 65 and up to 89, but now we can we know that these numbers basically can be represented in terms of some sine and cosine. So that means just we can add up some cosine and sine multiplied with some certain set of numbers. For example, in this case we just multiplied this one by 3 and this one by 10, and the very first one is basically the average of all the numbers. So it is very simple then, right? The first one is average number, and the second one is cos x, and the third one is sin x, and again actually cos x. We can think of this is basically a shifted version of cos x. So it is just some summation of some cosine numbers, and when we do the summation, this summation is becoming the very first numbers multiplied by 3 and the second was is multiplied by 10. So we can somehow we can say that these entire numbers can be represented by the 74, 3 and minus 10. Can you say that the 74 minus 3 and 10? And yes, somehow we can say, and this is exactly what this DCT does. The DCT mean discrete cosine transform. DCT discrete cosine transform. It means that we can convert a series of numbers, a sequence of numbers into another smaller sequence of numbers. Okay, a smaller sequence of, not exactly smaller sequence number, or let's say a sequence of numbers we can convert to another sequence of numbers of our choice just by by the summation of some cosine waveform or cos waveforms, and more appropriately discrete cosine. So that's why, because it is a transformation on discrete level, we are saying discrete cosine transform. Okay, so how it looks like ultimately you see this is our original number, and now we just we'll replace these numbers with these values, right, with this representation, geometric representation, 74 plus 3 cos x minus 10 sin x. So if we just calculate these numbers, and if we just have a figure on that, so let's say this is our x and this is our this y, or let's say these whole numbers. So then you will have this kind of continuous number, definitely, right? But then we need to sample it. Let's say periodically if we sample, so at a certain interval, so let's say this is one number, the second, third, fourth, and in this way. So ultimately this is becoming our new series of numbers. And if we just see this, so this is our original sequence of number, and this is our converted sequence of number. And if you see that it's a pretty approximated version of our original sequence. So and these things we can exactly do just by memorizing, or by just storing 74, 3 and minus 10. We don't need these real numbers, so greatly we can save the storage requirements. And so this is the magic of DCT, and there is another magic that we will see how it coming. But let's say we need to little bit not mathematics but mathematical expression, how mathematically we can actually represent this number, or in another word, how we do know this number 3 minus 10. We understand that's cosine, sine, but where this number coming from, how this number come, right? 10, 3. And so that's the things we can do some simple mathematical expression, and then we can do if you want to know that how it coming from. Okay, so let's say this is our original sequence of number fi, and this is our converted number fu. Okay, so that means all what we are doing is we are converting our one sequence of number to another sequence of number. And definitely this sequence of number, maybe we can say from 0, 1 and up to, I don't know, let's say maybe m minus 1. So that means there are m numbers in our sequence, original sequence, and we are converting to u equal 0, 1 and up to again m minus 1. So that is another another sequence of m numbers. So we had m numbers and we are converting to another m number sequence. Okay, now you can ask that why it is not less number. In fact, it will be we will see that how even the same numbers are converting to the same sequence of another sequence of numbers with the same length, but we will see that how this becomes useful. For this time being, let's say we have one sequence of numbers where we have m numbers, and we are converting with another sequence of numbers, still we have m numbers. Okay, so fi and f0. Sometimes we say, so this is time domain numbers, and we say this is frequency domain numbers. Okay, this is time domain and this is frequency domain. In another word, let's say this was our time domain sequence, and this is our frequency domain sequence. And you know why frequency domain sequence? Because ultimately when we do this cos x, so there is some frequency. Whenever cos sine, the cos 2 pi f, so this f become actually frequency. That if you have any cos of something, so if you just take 2 pi multiplied up with something, so that something basically your frequency. So that's why we say this is a frequency. Okay, so and then how we do convert, and you know that all we need is simple some summation of cosine waves. So where this cosine wave, or what this cosine wave looks like, this is exactly this one. Okay, so this is that one. So just we'll have something called cos of 2i plus 1 and u pi divided by twice m. This is this much of simple. That means we'll be taking each numbers and which numbers from our, for example, let's say very fast numbers I equal 0, 1, 2, and the second number, third number in this way, and we'll multiply that number with this cosine. Exactly what we had here. You see, we had cosine and then we multiplied with 3, we multiplied with 10. So this is exactly the same things. Okay. So, and this I, you see, we can change this I equals 0, 1 to up to m minus 1. And we are converting, to a new sequence of number that is fu, and u is also 0, 1, 2. So we also have this u, you see, that 0, 1, 2, 3 up to m minus 1. So we'll have to place this number accordingly. And then what we do these things for every, number. So that means when we are calculating for f0, so let's say we are calculating f of 0, so that means the very first numbers, our new numbers. So these things will be something like, summation, definitely, then we have, something like this, and then the summation is I equals 0 up to m minus 1 and cos this terminology and then fi, right? And fi means 0, you see. So that means for each number, we will have to, sum up. For each numbers that we are calculating the new numbers, we will have to, sum up some cosine and multiply it with this, our original sequence of numbers. So that means every time we are considering these are new numbers, each new numbers we are calculating, we are basically, taking the help of all of these numbers in some specific manner, right? So this is how we are calculating. So you can actually practice yourself that how we can calculate. Let's say you can just take one number 1, 0, 1, something like this, and you will be converting to another sequence of numbers. How we do that, you can do it, right? Anyway, so there is something like CU. There is a constant CU. Now this CU, what is this constant terms? It says that if u not equal to 0, so then it is 1, and if u equals 0, so that means at that time it is root 2 over 2. So that means for the very first numbers that will be our new numbers, for this one, our this CU value for the very first one, that is CU0, at that time the value is root 2 over 2, and for other number, for example f1 and up to m minus 1, for all of this number, this CU basically 1. Okay, and what is this m? M is that how many numbers you have. Okay, and this 2 is the constant. So constant, any constant. So in the beginning you need to calculate these constant numbers, and after that you can do these kinds of things. Okay, I'm not saying much more things on this, so we can actually say a lot of things about that, but for this timing, let's say this is okay. Now can you see that another perspective is as I increases, so that means as we go from the left to right sequence, we have this number of sequence, maybe 130, maybe 59, and in this way as we go with this sequence, as we go forward, so and then we are coming up with the new numbers fu, and similarly as you take, then first calculate f0 and then calculate f1 and then calculate f2, and in this way, now as you move to this rightwards or downward, whatever you say, f0, f1, f2, as you calculate the higher numbers, then you see these numbers is increasing, right? This 2i plus 1 multiplied by u, so this number, this is constant, pi is a constant, 2m is a constant. But how about 2i plus 1 multiplied by u? 2i plus 1 multiplied by u. So that means as u increases, so that means as we are going through like this, that we are having the higher numbers of this one, and as we go toward this, that means as we go from our older sequence, as we go to the rightward, that higher numbers of numbers, this is becoming increasing, right? So that means this terms increases. So this terms increases means this frequency increases. So frequency increases means, as you go like this one, so this frequency increases. So that means if we increase the frequency compared to this one, it looks like this one, right? So that means the frequency increases. Another increasing means there's more increasing, like this one. Okay, so this is how we can think of in another perspective, that how this is becoming increasing or decreasing. So anyway, so we understand this one, but this is actually one dimension, right? Only one dimensions that we are thinking. But how about our image? Our image is basically 2 dimension. That image has 2 dimension, right? If you think about it in this way, this is one dimension I, and this is another dimension j. So essentially, here now we will have Fij. So Fij means, let's say Ij represents your pixel coordinates, and this F is your, maybe we can say the brightness level of that pixels, right? So if you say in this way, that means in 2-dimensional DCT or discrete, cosine transforms in 2 dimension, we can think of like this way, that we have, one image and we are converting to another image called FUV. This is another 2-dimensional image. So this image we can say time domain image, and this image we can say frequency domain image. Now, how is the conversion looks like this two-dimensional, mathematically? It's essentially the same things, but now here we have both 1 dimension and 2nd dimension. So for the I and j, or for the u and v. So for the I or u, let's say we have this one, the cos 2i plus 1 u pi to m, the same. And for the another dimension, that is the 2nd dimension, we have now 2j plus 1, and definitely this one would be v, and this was our m in 1 dimension, and this is our n in another dimension. Okay, and this is exactly the same. It had fi, but now we have fij. It was fu, now we have fuv. So the same. So just we are converting to again another a 2-dimensional array of numbers to another 2-dimensional array of numbers. And now with constant terms, we had cu and the cv, it is the same things. Okay, in the same way, we will determine that as we calculated cu, we will calculate the cv in the same way. Now we got it. Okay, so again, now you see, we can think of in this way, that we are converting this fij to another image, that is fuv image, and we can think of in this pattern just by using this equation, 2-dimensional equation. Okay, now for image, we can think of that in both dimension. Let's say in this dimension and in this dimension, you have equal number of elements. So at the time, m equal will be n. So that's the simple thing. And in image, in JPEG, what you do is exactly we use 8. Okay, that is, we take every eight numbers. Okay, so even though your image is, let's say, large image, but we will consider this DCT transformation is 8 by 8 block. That means we will consider 8 rows and 8 columns. Okay, so this is rows and this is columns. 8 rows, 8 columns. So this will we can sometimes say this is 8 by 8 block. And then we'll consider another 8 by 8 block, and then we'll consider another 8 block until our image finishes. Okay, so if our image is large, we'll convert this entire whole image just by transforming each 8 by 8 block, and that will perform the DCT by following this one. So that means am equal n equal 8. At the time, we can just just replace all the m and n. So it had twice m, so twice m means 16. It had twice n, So twice n mean 16. And again, you see we had, root over mn. So that means 8 multiplied by 8, and then you just take the square root of that. You also calculated CUCV. So we also had these two. So this is a simplified form of our equation. Okay. So you now know it's very easily, and we will see that how we use it, but little later. But now another things we can say that, let's say you just convert fi to fe, right? So this is, we say, one-dimensional DCT, or one-dimensional discrete cosine transform. Now very interestingly, we can utilize the same form just to convert from the that we have new fu to go back to our fi. Okay, in the same way, in the same transformations we can do, and we can go back. So this is very pretty interesting things. Now see, we had fi, we converted to fu, but that this number is not exactly this one. It is an approximation. So when you convert this fu to fi, it will not be exactly same as this original one. So that's why we can say this is becoming an approximated or estimated version of that one. Okay. So the same things, when you convert this fij to fuv, then you convert back that fuv to this ij, it will not be exactly same, but an approximated version of that. So this one is simple discrete cosine transform, and this one we say inverse discrete cosine transform. Okay, IDCT. So the same. Then here we have the similar transformation. This one is our two-dimensional discrete cosine transform, and this one is our inverse discrete cosine transform. Okay, now let's go here. So this is, now we'll apply these things and we'll see that how it works. The very simple things. Let's say this is our entire image, and as you know that we will take is block by block. So let's say 8 by block, 8 by 8 block, 8 by 8 block. Somehow let's say we are now here. Okay, just this 8 by 8 block, and this is, let's say, gray level image, and so this 8 by 8 block, let's say the pixel values is 139, 144. So this one 153, and in this way this is 8 by 8 block. And what is this number? Is exactly 139, right? This very fast pixels, that is f00. So this is basically our 139. Okay, now how about this one? So this is, we are saying that f01 is basically 144. And if you go in this way, what is this one? This number is basically f77, that is 158, right? In this way. So this is our 64 number. It started from 00 and ended up with 77. Okay, so now if we just apply two-dimensional DCT on these numbers, okay, so that means you just now calculate f00 and then calculate f01, and in this way you just calculate f77. Now if you calculate this 64 numbers following this mathematical equation, this simple signal processing mathematical equation, then what we'll find this one. Okay, these numbers. So the very first number is 235.6, and so that means this one, and so this becomes 235.6, and the second number is minus 1.0, and the last number is minus 0.4, in this way. Okay, so that means this is, sometimes we say that from here to here we can say this is actually this number is basically discrete cosine transform coefficient, DCT coefficients. Coefficients means what are these numbers? Okay, new number sequence. So we said DCT coefficients. Now see, now can I look at these numbers? This is very interesting property in this number we have. Okay, what is this interesting property? Property is, see this number is 235.6, but how about this number? This number is really very small, that is minus 0 point something. And not only these numbers, even see these numbers, the whole are very small compared to these numbers, right? You see the number in this area is very small compared to these numbers, right? So in fact, if you more carefully follow, the most of the numbers is basically very small, but only, only maybe even, you see, that's entire within this range, that the same number types that we have now. These numbers are all very small compared to these numbers. So we had 64 numbers, but among these 64 numbers, only maybe these 16 and this maybe 14, that is only this 30 number is maybe a little bit significant compared to this one. Or in another word, we can say we can basically safely ignore this number and we can keep these numbers. Okay, so this is how now we can compress our image. Okay, so we can just ignore this number. But how we can ignore this number? There is, should have some mechanism, right? That how to eliminate this number. If this number becomes 0, then we can completely, remove. Because when something like comes 0, so this becomes 0 or 1. So at that time we can eliminate. So the process is very simple. Or in another word, we can say like this. See, so what is this place? Is basically, this place is F00 place, right? Now however, what is this place? This place is we are saying so this place is basically, we can say 00. We can, let's say 00 place, and the very last place is basically your 77 place in this example, 77. Now what exactly this location means? If you remember that as we go rightward, our frequency increases, or as we go in the downwards, our frequency increases. So that means this is the very beginning location. So at this point, our frequency is the lowest frequency. In fact, this one, the 00 location, is not a frequency. This is a very direct value, average value. So if you remember that one, just you go back, the very first one we had the average values, and other numbers is basically came up with cosine and sine. So why this the very first values is the average value? Because the very first is this value is 0. When something is cos 0, or so that means 1. So that means this, there is no sine cosine. Okay. So also you can see these things from here. The very first value is, let's say, if 0, and this is the 0, so that means this is 1 and this is 1, so there will be simply a number. Okay, so that is the summation of all of our numbers. So that's why the very first number is basically no frequency. That's the average number or average value. And as you go rightward, the frequency increases, because at that time these values will be increases. Or as you go to the downwards, that means row wise or column wise, whatever the direction, the frequency increases. So this is the highest frequency content and this is the lowest frequency contents. So this is very interesting. So that means in this image, as if you are in this location, we can say that what amount of frequency you have. Okay, so if this axis is this one and in this axis is this one, so perhaps this has a medium range frequency in both axes. Or in other words, how we interpret this frequency in the image. If we look at the image, where this image changes more, so that is image high frequency, and where this image changes very gradually, slowly, that is the low frequency content. For example, this area, you look, this area, the changes are very slow. That is called low frequency contents. But how about here? This is a very, at these particular places, or let's say you just go along this line. If you go along this line, so definitely you just come across some sharp and edges. So at that time the frequency is changes very much. Now see, in human eye, what we can see that our understanding, our perception, when if these are more sensitive than this one, because our human brain thinks, okay, there is some changing happen, but here if you have some distortion here, we understand more. So that means our human eyes are more sensitive to low frequency image content than high frequency image content. So that's why we will try to keep this low frequency contents, and we don't care much about these high frequency contents. Okay, now how we do so? In other words, we can say, understand that, let's say we will prioritize this low frequency contents compared to high frequency contents. So generally what we do, because this number is very big number, compared to this number, When we convert to in a Fij to FUV, this number is generally very big number. So what we can do, we can just divide these numbers. We can divide this number with certain numbers. Okay, definitely there are some research happen that what number we can divide by, but we will divide by some numbers. So when we divide these numbers, so that is the problem. The problem is we'll try not to hamper this low frequency content usually compared to our high frequency contents. Or in other words, we can divide these numbers by larger numbers comparatively compared to these numbers. Okay, now how we divide that, there is certain research on that, and it says something like this. Let's say, how about let's say this is our something like the very first numbers, that is 00 number, will divide by 16, and the very last number, that is 77 number, will divide by 99. Or in a nutshell, you can see that these numbers is basically are larger compared to these numbers, because we know that this is our low frequency content, and so we'll divide that low frequency content by smaller numbers, and this will we'll divide by larger numbers because these are high frequency contents. So even though it becomes 0, so we don't care that things, we can ignore actually. Okay, so these numbers sometimes we say quantization table. Okay, quantization table. And why we are saying quantization? Because when we divide, we are basically quantizing our numbers in some sense. Okay, and there is another table like this. So sometimes we use this table, sometimes we use this table, whatever it is. You can use both table, but let's say this is widely used, but depending on some applications you can also use this table, but whatever, this is called quantization table. So ultimately we came to a certain, at a place that where we can understand JPEG standard. Now JPEG basically works with both color image and grayscale image, but if we use with a color image, we'll have to convert to some model, right? That maybe RGB model or maybe YUV model, whatever it is, it works for both. And this is basically target photographic quality and suitable for many applications, for example satellite, medical, general photography. So these are the things. So how we do so? Let's say we have RGB model, or let's say we can convert RGB model to YUV or YIQ model, whatever it is. So and then if we have RGB model, so definitely we'll just first process R model, that is R plane, then G plane, and then B plane. Okay, because every two-dimensional plane we will process at one time, because this is how JPEG works, right? We cannot process these three things together. So if we convert to YIQ, definitely we have three plane: Y plane, I plane, and Q plane. If YUV, we have Y plane, U plane, and V plane. So whatever it is. So anyway, so let's say RGB. Think about RGB. So that means we just take first R plane, and then we do this mechanisms, this process, and after that we'll take green plane, and then we will do again this process, and then blue plane, again this process, then we will done. So how it looks like then? See, we just take every 8x8 block from that particular plane that we are talking about. For example, so let's say red plane. So we just take, this is our Fij, and then we convert by two-dimensional DCT, and then we will have FUV definitely for each 8x8 block. So that means when we take a particular plane, we'll first take 8x8 block, next 8x8 block, next 8x8 block, but here we are showing for only one 8x8 block. And then we'll do this quantization, and quantizations means we'll divide these numbers by the quantization tables, and then we'll have this FUV, right? That. And after that, what we have, let's say we first go there, then what we had. When we divide these things, see that this is our image coming, and then let's say this is our 8x8 block, one block. And so this is basically our, when you convert these things into DCT, so this is our, DCT coefficient matrix. That means 8 by 8 converting to another 8 by 8, just two dimension DCT. So this is becoming our FUV, right? And now we supply this, let's say this one, this is our, which one is this one? Let's say this is our, quantization table. Okay, so there are many quantization table actually. So here, for example, we talked about something like this one, that is 16, 11. Even you can have even another quantization table. Even you can choose, what you want. But let's say this is that one. Okay, this is our quantization table, and this is our discrete cosine transform. Now, if we divide, this table by this table, that means element wise, we'll divide, this 185 and this, 04, this 06, 02 by these corresponding numbers. Okay, 001, 001, 001, 016, and in this way. So if you convert, this one, so if you divide this one, let's say this is our quantized, coefficients or quantized number. Ultimately, you see, this is 182, 044, 07, 003, and most of other numbers are basically 0000. Only few numbers are, few numbers are significant. Now what we do, you see, there is an interesting pattern. Now it says that, most of the numbers 00, but how about, if we just, collect these numbers in a zigzag pattern, and just we will follow some specific zigzag pattern like this. Let's say this is our, converted, and after quantization, this is the table. But if we just collect the numbers in such a way, let's say first number is okay, and then we will go here, we'll take this number, and then we will go here, we'll take this number, and then we'll go here, we'll take this number, and then here this number, and then we'll take this number, and then we take this number, then take this number, and then take this number. If we just follow this kind of zigzag pattern, then what will happen is something like this. You see, 182, 44, 7, 12, 13, 7, 3, 35, 0, 5, 3, and then you see, you come at certain point, and after that all number becomes 0. So that means that, after conversion and division, okay, after we convert and then we divide by these quantized tables, and let's say we have these numbers, then okay, these numbers is basically, is come, and then you take zigzag pattern, then most of the numbers are basically, you first see all the non-zero numbers, and then all the remaining numbers is zero numbers. So the same as this one. Okay, the same as this one, just first few numbers are your non-zero numbers, and then all numbers are zero numbers. Now think, if we apply some sort of, run length coding, if you remember, if we apply run length encoding onto these numbers, that means is all these numbers you can basically, just convert all of these numbers just by using maybe how many zeros, maybe let's say we have 30 zeros. Okay, so let's say 30 zeros, just using this one, right? So that's the mechanism how we do. So there are three things is highly playing role. The one thing is that when we convert to a DCT, most of the numbers becoming very non-significant, and then we divide this number by quantization table, we made most of this number zeros, and then we apply run length coding, and then it become compressed. So that's the idea in DCT. So this is the process that you understand that now. So we convert to a DCT, and then we have this one, and then we divide by quantization table, we have this quantized number, and then you do the zigzag pattern, and then you have, something, all the numbers you converted by run length coding. So except, the very fast numbers, because very fast numbers is a larger number, and there is no frequency associated with it. So just keep this number as it is, and all other numbers we do zigzag coding. Okay, so anyway, for the very fast numbers, we use some specific coding called DPCM. We use a DC or direct current. So this we will see later when we study, audio coding. So anyway, so after we have those numbers, and then we further apply Huffman coding, because if we do Huffman coding, we can further compress that data. Definitely, we add some header and tables, and then we have, just, JPEG image. So this is what we do in JPEG, image conversion. And this is not an very complicated things, but there are various things we need to accumulate together. Okay, so first things, we need to convert color space if we need to. That is YIQ or YV something. There is something like subsampling. We did not study this one. Then we did DCT, and then we did quantizations, means dividing by certain quantization table, and then we did zigzag pattern to collect our numbers. And for the very first numbers, we use certain coding technique called DPCM, differential pulse code modulation, and we'll see how it works later on. And all other numbers we used RLE, that's why we are saying AC component, means where there is frequency, and DC means there is no frequency. And anyway, after that we used some sort of entropy coding, for example Shannon-Fanon or Huffman coding, and we get done. So that's how JPEG works. Okay, now there is something modern techniques called JPEG 2000, is also very interesting techniques, say JPEG 2. We talk 1 minute or 2 minutes on that. So JPEG 2 is a simply extension of extension JP2 is the latest series of standard of JPEG. Still a very JPEG original JPEG is still we use a lot, but also JPEG 2000 is also great things. So it uses basically called wavelet technology, and the focus is something like that. If we look about our image or numbers, whatever it is, there are many places where this kind of abrupt changes happen. Most of the times this kind of slow changes, but there are this kind of slow changes, but there are certain places where the image goes very abrupt changes, that is called transient changes. So to capture these transient changes, we use wavelet technology, something the signals look like this one. Okay, and because this wavelet itself look like very sharply transits, so what we can do, we can actually scan this entire signal with this wavelet, and we can see where this sharp changes happen. So we can have some mathematical transformations using that one. So by just considering that kind of situation, we can achieve better compression than JPEG, and there are certain other useful things that we can do. For example, we can do region of interest coding. What is region of interest coding? See, for example, image is, even though one image, but it has certain different regions that we are more interested. For example, when we are thinking about this lane detections, so we are basically interested in this lane, we are interested in this lane, we are interested in this divider. So this kind of region of interest things can be better done if we have this JPEG 2000. Also, we can work on computer generated imagery. For example, you see these are computer generated image, it's not the real image. So this kind of things we can do. We can handle these kinds of multimedia data by using JPEG 2000 conversion. So whatever it is, so we finished our the entire things. So now I believe that you got very thorough idea on this multimedia data compression, especially for image perspectives. We studied lossless compression techniques. Also, we studied lossy compression techniques, and we studied RLC and variable length coding. We saw that how DCT plays a role in JPEG compression. Basically, the JPEG standard is not just one thing. There are multiple concepts together, and then we can achieve these JPEG stuffs. But I believe that from multimedia perspectives, this is sufficient for you to understand these things. Now, rest of the things you can practice. So I know this lecture is a little bit longer, but I believe that you enjoyed that. So I didn't want to take it to the next week, in fact. Okay. So in the next week, what we can do, maybe I can give you some demonstrations on this, JPEG and this maybe this code transformation and coding a little bit, and then we can start with some other things. Okay. So so see you in the next week.